Hello, welcome to the last lesson of Chapter 8. Woohoo! This is called logarithmic differentiation. So sometimes we have really complicated looking functions that we're asked to take derivatives of. That looks gross. And you're like, there's a product rule, and there's a quotient rule, and there's a chain rule, and there's a lot going on. So there's a method of logarithmic differentiation that we can use that reduces the number of steps, makes it much simpler to actually calculate the derivative. And what we do is we take the natural log of both sides of your function. So don't just do it on the right, but you have to do it on the left as well. Expand using your laws of logarithms, and then you're going to differentiate implicitly with respect to x, and then just isolate for y prime. All right, so what does that look like? So step one, we're going to take the natural log of both sides. And I'm just going to write this other guy, the root of x squared plus 1 to the power of a half, all over x squared plus 2 cubed. And then step two, we're going to expand out that right side. There's nothing to do on the left. Okay, so we have ln y is equal to ln e to the x plus ln, because we have a product there, x squared plus 1 to the half, and then we have a quotient, so subtract ln of x squared plus 2 cubed. And before I differentiate, I'm going to go one step further and move all of those exponents to the front using the power law. So we have, that's a little sloppy, x times ln e plus 1/2 ln x squared plus 1 minus 3 times ln x squared plus 2. Now we have expanded it out, and what's left to do next is to differentiate. So just before I differentiate, I'm going to notice that I do have a ln e. So pay attention to this. What is ln e? That's just log e base e. So this is just equal to 1. Okay? So we could just simplify that out before we move on to the differentiation step. So we are differentiating implicitly here. What is the derivative of ln of something? Ln u. It's 1 on u, so 1 on y, multiplied by the derivative of the argument. So that would be y prime. Is equal to the derivative of x is 1 plus, now we have 1/2 as a coefficient being multiplied to the derivative of ln of your argument. So 1 on your argument, 1 on x squared plus 1, multiplied by the derivative of the argument, which is 2x. I'm going crooked here, minus 3 times 1 on the argument, this time is x squared plus 2, and the derivative of that is 2x. And now we're going to just tidy up a little bit before we move on to isolate for y prime. So I have y prime on y is equal to 1 plus, I'm going to see that those 2's could cancel, and that would leave me with x on x squared plus 1. And then on the last term, I have minus 6x on x squared plus 2. What we're going to do next is isolate for our y prime. So that means I'm going to need to multiply by y and move my y to the other side. So this is our step 4. So I have y prime is equal to 1 plus x on x squared plus 1 minus 6x on x squared plus 2, all multiplied by y. However, what is y? So right at the very beginning, they define y as this beautiful ugly function that we started with. So we're actually going to replace y in that very last line with that term. So therefore, y prime is 1 plus, actually I might put it in the front. Sorry, I think it'll look a little prettier in the front. Okay, so we have e to the power of x squared plus 1, the root of it, on x squared plus 2 cubed. And that is being multiplied by 1 plus x on x squared plus 1 minus 6x on x squared plus 2. And that's it. I'm not going to try and get that tidied up, okay? We're not going to try and make common denominator and make it look prettier than that. That's as far as we're going to go. So not that hard. Okay, example 2. What do we got going on here? So step 1, we want to take the natural log of both sides. So ln y is equal to ln of x times sine x on x squared minus 1. And it's to the 5th root. So this would be to the power of 1/5. So now I'm going to tidy this up. Oh, let's use a different color because it's more fun. Green. Here we go. Step 2. Ln y is equal to, we're going to put that 5th in the front. And then I'm going to expand out with my log laws, but make sure you have brackets on that because the 5th was to the whole thing. So we have ln x plus ln sine x minus ln x squared minus 1. Okay, so we're all expanded out. If you wanted to, you could put the 5th all the way through. It's kind of your thing. I just liked it factored out. I think it's good to just leave it factored out. It'd be tidier in the end. Okay, so what is step 3? Step 3 is where we actually get to differentiate. So the derivative of ln y is 1 on y prime is equal to 1/5 multiplied by the derivative of ln x, so 1 on x, plus the derivative of ln sine x, so 1 on sine x, multiplied by the derivative of sine, the argument, which is cos, minus ln, no ln. Oh, gone with the lns. 1 on x squared minus 1. And that needs to be multiplied by the derivative of the bottom, which is 2x. And so there's my derivative. Is there much for us to tidy up? Not a ton. We could say that cosine sine is cotan. So y prime on y is equal to 1/5. 1 on x plus cotan x. So that's about all we could do for that. And then we're going to multiply both sides by y. And find our final answer. So what was y this time around? Oh my goodness. Remember y was this ugly root thing? Yeah? Maybe we'll use red. So y prime is equal to 1/5. What is y? We're just going to replace this y right now as I go so we can reduce our steps. The 5th root of x sine x on x squared minus 1. And then we have our ugly 1 on x plus cotan x minus 2x on x squared minus 1. And that's it. That one is done. What do we got next? Hey? So logarithmic differentiation can also be used when a function has a variable in both the base and the exponent. So here's a really funky function. X to the power of x cubed. Okay, so we're just going to go through those 4 steps again and see how that works when we have these variables in 2 spots. So we're going to take the natural log of both sides. Ln y is equal to ln x to the power of x cubed. And then we will use our log rules to simplify this. So we can use our power rule to bring our x cubed down. And what that ends up being is that we now have a product when we go to differentiate. So let's go ahead and give that a go. Step 3, derivative of ln y is 1 on y prime is equal to. So here's our product rule, 1 d2. So the derivative of ln is 1 on x plus 2 d1. There we go. 1 d2 plus 2 d1. The product rule is so much fun. 1 d2 plus 2 d1. Okay, so now what could we do to tidy up? It looks like I could cancel out one of those x's. So I'd have x squared, and then I would just have plus 3x squared ln x. Now we're going to multiply both sides by y and replace the y. So step 4, what do we have here? We have therefore y prime is equal to, what was y? So y was this funky x to the x cubed, and we're going to multiply that by x squared plus 3x squared ln x. All right, now we're going to actually try and tidy this up a little bit more. I actually have a common factor of x squared on this piece, this tail. So if I was to take an x squared out, what would I be left with? 1 plus 3 ln x. And then this has to be multiplied to this funky x to the x cubed. So then we would end up with something like this. And then because that front end is being multiplied and they both have a base of x, I could in fact use my exponent law that says I could add those pieces, those exponent pieces together. And then we would have a little bit more simplified factored form like this. There it is. All right. So how about you guys pause, because we're not quite having enough time to do part B without going to a new video. So give this one a go before you hit play on video number 2.